कर दिया सर.
Yes, Abhishek sir, I think we can start now.
Okay.
Wait a minute, let me check. Please start.
A very good morning to one and all present here. I, Abhishek Singh Verma, on behalf of Sarda University, welcome you all on this 9th keynote session on 4th one-week International Faculty Development Program on Recent Advances in Computer Science and Allied Domains 2022. I hope you have enjoyed the sessions delivered so far. Today we have with us Dr. Om Pal from Ministry of Electronics and Information Technology, Government of India. Dr. Om Pal received B degree in Computer Science and Engineering from Dr. B.R. Ambedkar University, Agra, MBA in Operation Management from IGNOU, MS in Research in Field of Cryptography from IIT Bombay, and PhD in Field of Cryptographic Key Management from Jamia Millia Islamia, New Delhi. He has more than 19 years of academic and research experience in various areas of computer science. He is currently a scientist D at Ministry of Electronics and Information Technology, Government of India. He has involved and worked on many research projects of national interest. He worked at Center for Development of Computing as a senior technical officer and as an IT resource person in National Thermal Power Corporation, NTPC. He has filed patents on conditional access system and cryptographic systems. He is also a certified ethical hacker. He has published many research papers in international journals, including IEEE, Transactions, Springer, Elsevier, and international conferences of repute. He served as a guest editor in Multimedia Tools and Applications Journals and Journal of Food Quality. He is also an editor for CRC Press, Taylor and Francis Group book series, and Elsevier book series. He has been nominated in the board of reviewers of various peer-reviewed and refereed journals. His research interest includes cryptography, quantum computing, cybersecurity, blockchain technology, theoretical computer science, and cyber law. With these words, may I request Dr. Om Pal to take over and the gathering. Sir, please.
A very good morning. वीडियो शायद फिर नहीं आ रहा एक्चुअली कुछ टेक्निकल प्रॉब्लम है गौरव सर वीडियो आ रहा है सर
नहीं सर वीडियो नहीं आ रहा स्क्रीन शेयर कर पा रहे हैं
हाँ सर स्क्रीन तो शेयर कर पा रहा हूँ मैं सर एक बार मैं रिजॉइन करता हूँ
ठीक है सर वी आर वेटिंग फॉर Yes, sir, your video is visible. Gaurav, sir, make him co-host. Yes. Now, sir, your video is coming. You please check once for screen sharing also.
Now.
Yes, screen is coming, sir.
Yeah.
Yes, it is coming perfectly, sir.
अभी मेरी तरफ क्लियर नहीं हुआ है स्क्रीन जस्ट
Might be some bandwidth related issue, sir.
जस्ट अभी मेरी तरफ
We
क्लियर
can
नहीं
see it clearly.
है सर, आपकी तरफ है पर मेरी तरफ क्लियर नहीं अभी हुआ है ये।
Clearly, this is a PDF file, not a PPT.
नहीं तो उससे कोई फर्क नहीं पड़ेगा सर।
फर्क नहीं पड़ेगा ना?
उससे कोई फर्क नहीं पड़ता।
ठीक है, ठीक है, ठीक है।
पीपीटी में एक बार पीपीटी करता हूँ शेयर, मतलब इससे कोई इशू है तो पीपीटी एक बार। सर जस्ट कर रहा हूँ।
Yes sir, it is visible to us.
ओके सर, बस मेरी तरफ अभी विजिबल नहीं है ये। एक्चुअली कुछ तो इशू हमें लग रहा है, कुछ प्रॉब्लम है।
Sir, you can share your PPT with us. We can share it. Maybe it will.
Okay. जस्ट लास्ट ट्राई है, उसके बाद मैं आपको शेयर कर दूंगा। यदि मान लो नहीं होता है ना, तो अभी मैं अंकुर सर को
फिर
शेयर
आप
कर दूंगा।
whenever you will say next ना, ये गौरव सर will do it for you.
हाँ ठीक है, ठीक है, मैं अंकुर सर कर देता हूँ मैं।
ठीक है सर, आप मुझे
व्हाट्सएप पर मैं शेयर कर रहा हूँ सर। आप
जी आप कर दीजिए, मैं फॉरवर्ड कर देता हूँ।
श्योर श्योर।
Received sir, received sir.
Okay.
Gaurav sir, please check. Got it sir? Sir, is it visible to you now? हेलो सर, विजिबल है आपको भी?
यस, हाँ वो विजिबल है। ओके, एक्चुअली कुछ तो मेरी तरफ से कुछ टेक्निकल प्रॉब्लम, आई एम वेरी सॉरी। अब पता नहीं क्या दिक्कत है, एक्चुअली मैं ऑफिस में हूँ, हो सकता है कुछ प्रॉब्लम हो, लेकिन ये कभी इतना टाइम नहीं है कि टीम को बुला सही कराऊं। पहले चलिए
ठीक है सर, now you can continue sir with this only. You can say next whenever you will say next. Gaurav sir will move to the next slide.
Sure, sure. Okay, so a very good morning to all of you. First of all, thanks to Ankur sir, Arut sir, Gaurav sir for this invitation. So today topic of this talk is quantum cryptography and its security. Actually, in this talk, we will talk about quantum computing and its security. Also, why we are moving from classical computing to quantum computing. What are the advantages of quantum what are the advantages of quantum computing over classical computing? Is it audible, Gaurav sir?
Yes, sir, but
Yes,
it's
sir.
slightly missing somewhere.
Okay, okay. Sir, visible है slide?
Yes, sir.
Is it visible?
Yes, sir. Yes.
Okay. So first we will see what are the advantages of quantum computing over classical computing, and what are the limitations of this quantum computing. We will also see that actually in classical computing we divide problems in two categories: uh, p problem and np problem. P problems are solvable in polynomial time, but np problems are verifiable in polynomial time, but they are not solvable in polynomial time. So means exponential complexity is required to solve the np problems in classical computing. But in quantum computing, we will see that there are few problems which have exponential time complexity in classical computing. What these few problems सर, ये काफी बार बार प्रॉब्लम हो रहा है, पता नहीं क्यों हो रहा है एक्चुअली।
Sir, can you
हम
connect
इसको
with your
अच्छे से,
mobile phone?
हाँ बिल्कुल, मोबाइल फोन से मैं कनेक्ट करता हूँ।
मोबाइल फोन से कर
मोबाइल
लीजिए
फोन
सर,
से एक बार
स्क्रीन
मैं
यहाँ
ट्राई
से आपको मिल ही जाएगी, वो कोई दिक्कत नहीं होगी।
ओके, ठीक है, जस्ट मैं अभी एक
You
बार
can
ट्राई
connect
करता
via two devices even.
हूँ। ओके सो
You first connect, sir. We are waiting. Not an issue.
ओके।
Hello, good morning, ma'am.
Okay, just okay. So actually, there are two types of problem: P problems and NP problems in classical computing. So actually, we will see that a few problems are solvable. Means a few NP problems are solvable in polynomial time in quantum computing environment. And we will take one example, and we by that example. We will see that the complexity of that problem is exponential in classical computing, but that can be solved in polynomial time in quantum computing. Okay, next slide, please. Okay, So actually, before coming on quantum computing, first we see one example. Actually, this is not really related to quantum computing, but this is real life problem. Let's say there are 3 points: point A, point B, and point C. Uh, one person want to move from point A to point B, but that person is not aware about the water transport as well as air transport. So first, that person should go to point C, then via point C to point B. So means let's say initially he used cycle, then motorcycle. After more inventions, he used car. So means by invention, he is increasing his speed. He is reducing his time, or we can say that he is reducing the time complexity for reaching from A to B. After that, train, bullet train. But means for each invention, there is a limit. For this speed up. Now, if he can devise a water transport or air transport, in that case, he can save a lot of time. I think that time will not be comparable to that road transport time complexity. So actually, in same way, actually we solve problems in classical computing. Next slide, please. In we solve we solve problems in classical computing. Actually, we can also solve the same problem in quantum computing, but by using a different approach. Next slide, please. Next slide. So actually, the solving mechanism of same problem is different in classical computing and in quantum computing. What result means output will be same. Means if we are solving that problem in classical computing and we are solving the same problem in quantum computing, then final result will be same. What solving means approach of solving this problem is totally different. So now first we see what is the quantum computer. Actually, a quantum computer is any device for computation that makes direct use of quantum mechanical phenomena such as superposition and entanglement to perform operations on data. So actually here I'm using the term superposition and entanglement. Actually in next slides we will see what is this superposition, what is entanglement, and how they are helping in quantum computing to do faster computation. Okay. In next definition, a quantum computer is a machine that performs calculations based on the laws of quantum mechanics, which is the behavior of particle at the subatomic level. Actually, in classical computing, there are only two options, 0 and 1. Actually, we perform operations 0 and 1. Other than these two base state, there is no third option. Means if we can uh, do computation uh, means on 0 and 1 as well as on few other valid state. So in that case we can accommodate more information as well as we can do more means faster calculation. Let's say let there is a electron means for this quantum quantum particle we can use upward direction, let's say for 0, downward direction for 1. Means if electron is in upward direction, then we can say it denotes 0. If it's at downward direction, then we can say it's denote 1. Now assume that if the angle of that electron is at 45 degree, means it's not at upward direction, not at downward direction, then whether it will represent 0 or whether it will represent 1. Actually for this we will see in next slide. Actually in classical computing there is no third choice other than 0 and 1. We have to do the computation on 0 and 1. But in quantum computing we can also do the calculations on valid states. Next slide, please. We can do computation in quantum computing on these valid states. So now for representation means actually in quantum computing we can use electron, we can use atom, or we can use polarized light. Actually we can use any mechanical this quantum phenomena for any for any quantum particle. So actually, just we have to represent the information. Uh, let's say there is a polarized light. After passing the polarized light from this polarized filter, let's say uh, if there is a horizontal polarization, then we can denote this information as 0. Now if it's a vertically polarized, then we can represent this information as 1. So means, like our classical computing, if the transistor is on state or in discharge state, so in classical we use 0 and 1. So here we can also represent information in as well as 1. So if the angle is 0 degree, if the angle is 0 degree, it means, let's say the orientation is horizontal. If the orientation is horizontal, then if we measure this information, then we get the 0. If it's vertically oriented, if the angle is 90 degree, in that case we will get information as 1. If the angle is at 45 degree, then it's not representing 0, it's not representing only 1. In this case, it is representing both 0 and 1, and with equal probability. If the angle is 45 degree, then it means exactly 50% time we will get 0 on measurement, and 50% time we will get 1. So means here, this valid state, this superposition state is 0 and 1. Next, please. So actually, in classical computing, the smallest unit is bit. In quantum computing, the smallest unit is qubit. So this is the notation. Let's say nuclear spin orientation of atoms in nucleus in magnetic field. If it's upward direction, then we let's say we dot cat 0. So this symbol is the cat 0. If the direction is downward, then we can note it's a cat 1. So here cat 0, cat 1 means these are two qubits. So actually, we can represent information by using the this physical, or we can say the quantum property of this uh, quantum particle. Next slide, please. Okay, so if the angle is 0 degree, or if the angle is 90 degree, let's say if the angle is 0 degree, then if we represent this as cat 1, and if the angle is 90 degree, then if we represent this cat 0, it means state is alpha cat 0 plus beta cat 1. Here alpha square is the probabilistic amplitude of cat 0, and beta square is the probabilistic amplitude of cat 1. So alpha square plus beta square equal 1. So now, if the orientation of that polarized light, let's say it's a horizontal. If it's horizontal, if it's horizontal, then in that case, value of beta square will be 1. If the value of beta is 1, means value of alpha will be 0. So the probability of 1, this cat 1 will be 1. Now, if the angle is 90 degree, then value of alpha square will be 1. In that case, probability of cat 0 will be 1, and probability of cat 1 will be 0. So now if the angle is between 0 and 90, let's say it's 45 degree or 60 degree. In that case, the value of alpha square will be more than 0 and less than 1, and value of beta square will be also sorry, greater than 0 and less than 1. So now slide, please. So voice is please, one voice from while, and okay, okay. So,
Yes,
Gaurav,
sir.
uh,
Yes, sir. We can hear you now.
is it audible?
Yes, it is better, sir.
Okay, okay, okay. So
Please
here,
close the volume for second system, sir.
okay, 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 fine. So actually, here there are two base state, cat 0 and cat 1. Other than this cat 0 and cat 1, we can use valid state alpha cat 0 plus beta cat 1. So here we can accommodate more information on these valid states. Also, we can do computation on these valid states. Actually, other than this base states, 0, cat 0 and cat 1, we have more states. These states are called the valid states, alpha cat 0 plus beta cat 1. So we can do more we can do computation on these valid states. It means we can achieve higher speed. Next slide, please. Okay. Now, what is superposition and multi-qubit? So, first, superposition. Quantum particle may remain in a third state, which is neither excited state nor ground state. Actually, uh, mm, for representing information, we can use ground state for cat 0, for means excited state for cat 1. Means now, let's say it's not excited state nor ground state. In that case, means angle is between 0 and 90 degree. So actually that state is the superposition state. So we can do the computations on these superposition states. So actually quantum computing algorithm, they can perform the computation on these superposition states. After performing the computation on these states, we can measure the results. Then final result means final outcome will be same. So any superposition state we can represent like this: cat psi equal alpha cat 0 plus beta cat 1. Now we can also use multiple qubit. We can combine more than one qubit, and we can get the superposition vector on these multiple qubit, and then we can also perform operation on this superposition vector for multiple qubits. So if the one qubit is alpha cat 0 plus beta cat 1, another qubit is gamma cat 0 plus eta cat 1, then after that the superposition vector is this alpha gamma cat 0 0 plus alpha eta dot dot this. So here, what is the alpha gamma? So here alpha gamma square, this is the probabilistic amplitude of cat 0 0 means alpha gamma square is the probability of being cat 0 on first qubit and cat 0 on second qubit. Next slide, please. Okay. Now, quantum entanglement. Actually, like the superposition, actually, this entanglement is the ability of quantum systems to exhibit the correlations between two or more objects, even though the individual objects may be especially separated. Actually, in this, two quantum particles are correlated, means positively correlated or negatively correlated. So, if they are negatively correlated, then the results on these particle will be just opposite. So now let's say if one particle is situated in our galaxy and another particle is situated in another galaxy, in that case, if we perform the one operation on one particle, let's say if we measure the one particle in our galaxy and the value of that particle is 0, then immediate we will get the just opposite result on that entangled particle which is situated in another galaxy. So the output means result of on that another particle will be 1. One more thing, actually there is sudden change. Actually here it doesn't obey the law of speed of light. So actually just if we are doing something change on one particle, then without any delay, uh, so you will get the immediate change on another particle. So this is called the quantum entanglement. Next slide, please. Okay, now actually in classical computing we use gate for operations, and in quantum computing also we use quantum gate. So actually first we see what is this the quantum gate. Actually it is a setup of quantum mechanical equipment which converts the present quantum state of quantum particle into a new quantum state. Actually, let's say if the orientation of that polarized light is horizontal, means the angle is 0 degree. Now, if we pass that polarized light from this mm, quantum mechanical setup, this quantum mechanical equipment setup, after that, if we are getting the new angle of 90 degree or 45 degree, it means we change the state of that quantum particle from 0 degree to 45 degree or 0 degree to 90 degree. So actually this setup, quantum mechanical setup is called the quantum gate. Actually, this setup uh, shifts the state of the quantum particle from 0 degree to 45 degree. So actually this is called the quantum gate. Now, first we talk the next, first quantum gate, that is the C naught gate. Control NOT gate, actually a gate which operates on 2 qubits. One qubit is called the control qubit and another qubit is called the target qubit. This gate is known as the C naught gate. The property of this gate is this: if the bit on the control line is 1, means at input side, if the bit of the control line is 1, then it inverts the target line at output side. So from this table we can see, if we see the last row, if the control line means the value of B is 1, then at output side you will see the value of A dash is 0. Actually it inverts the value of A from 1 to 0. Next slide please. Next slide please. Okay, now next gate is the head-mart gate. Actually, head-mart gate is used for superposition. We can shift any quantum state from base state to superposition state by using the head-mart gate. So a simpler gate involves one qubit and is called a head-mart gate. So by using this head-mart gate, we can shift the base state to superposition state. Let's say if the here we denote head-mart gate by H. So if we supply information cat 0, then after passing this cat 0 to this head-mart gate H, what we will get? We will get the superposition state that is cat 0 plus cat 1 upon square root 2. So this is also called cat plus. So here the interesting thing is this: probability of cat 0 as well as probability of cat 1 is equal. Actually, this is at 45 degree. So if you measure after this first head-mart gate, then exactly 50% time you will get 0 and 50% time you will get 1. Now, if you apply another head-mart gate, then you will get the initial input. Means if you apply the same two head-mart gate one by one, then if the input was cat 0, then output after two head-mart gate will be cat 0. So now, if the input for first head-mart gate is cat 1, then after this what we will get? We will get cat 0 minus cat 1 upon square root 2. This state is called the cat minus state. So here the probability of 0 as well as 1 is also same, but the angle is different. Angle is 135 degree instead of 45 degree. After applying another head-mart gate, we will get the same information as cat 1. Actually, this gate is used for to shift the quantum state to superposition state. Next slide, please. Next slide, please. Okay. Actually, we use this head-mart gate for random number generation. Actually, in classical computing, there is no perfect algorithm which can generate the random number. So this head-mart gate can be used to generate the quantum random number generation. So here, as I said, if we use head-mart gate and we just supply cat 0 as an input, then what we get? We get cat 0 plus cat 1 upon square root 2. So here the probability of 0 as well as 1 is same. So means there is 50% chance of 0 and 50% chance of 1. So on this measurement, M denotes for measurement. So means almost same number of 0 and 1 will be received. So actually this is the Qiskit programming. QC equal quantum circuit 1 means here we are giving one qubit as input. QC dot H 0, H denotes for head mod gate. 0 means just here we are giving cat 0 as input. So qubit 0. QC measure all. Job execute QC backend Quasar simulator source 1000. So 1000 times we are repeating this process. After this, just we are plotting plot a histogram. Then we are plotting this. So almost 50% time here we are getting cat 0 and almost 50% time we are getting cat 1. So actually we can use this head mod gate as a quantum random number generation. Next slide please. Now, quantum computing power versus classical computing. Quantum computing operations are reversible. What classical computing operations are irreversible. This is the first difference. All qubits can be operated simultaneously in quantum computing, hence exponential speed up is guaranteed. Classical bits are operated sequentially. One more thing, actually in classical computing there are only two options 0 and 1, but in classical this quantum computing we can use superposition states for our computing purpose. Next slide please. Okay, now we will take one example. The complexity of that example is exponential in classical computing. What we can solve that problem in polynomial time in quantum computing. So before coming on that problem, just first we see a few mathematical jargons. We will use this. Let's say UF is a black box. UF is a function. Here we are giving input cat x, cat y. So actually cat x is a control line. Cat y, this is the input for target line. After passing cat x, cat y to this UF function, now at output side we get cat x, cat y XOR fx. So here the bit on control line is same, cat x, cat x. There is no change on control line, but at target line here there is a change. We are giving cat y as input on target line, but on output side, what is the target line output? This is y XOR fx. So here the output on target line is dependent on x as well as y, or we can say y as well as on fx. So fx is a function. Now assume if the value of y is 0, then cat x, cat 0, then it will be cat x, cat fx. Or if a value of y is 1, then it will be cat x, cat fx dash. This is just a complement. Okay. Now x belongs to 0, 1, n means the length of x is n, and there is a this function f 0, 1 to 0, 1. Okay. Now assume that if fx is a constant function, then always we will get fx equal 0, or always we will get fx equal 1. So if fx is a constant function, then what we will get? We will get uf cat x, cat y equal cat x y XOR 0. It means cat x, cat y. If fx is a constant function and the value of fx is 0, then always we will get the same output as input. Means cat x, cat y is input and cat x, cat y is output. Now if fx is a constant function and value of fx is always 1, in that case what we are getting at output side? At output side we are getting cat x, cat y dash. It means just opposite of y. So now we will use this. Next slide please. Next slide please. Okay. Now actually Dutch problem. The aim of the Dutch problem is to find out if a given black box oracle represents a constant function or a balanced function. Actually, inside a black box, there is a function fx, and we don't know whether fx is a constant function or fx is a balanced function. Actually, if fx is a constant function, then always we will get the same value for fx. If fx is a balanced function, in that case, exactly 50% time we will get fx equal 0, in exactly 50% time we will get fx equal 1. And from a trusted source, we know that either fx is a constant function or fx is a balanced function. Actually, also there is a possibility of a third choice, but we uh, ignore that choice. Actually, from trusted source, we know that only two choices are available for this function, whether it is constant or balanced. Okay. Now, assume if fx equals 0, now value of fx is either 0 or 1 for all 2 to the power n possible value of x. Let x and the length of x is n. So if the length of x is n, then total possible values for x value 2 to the power n. Means for each bit there are two choices, 1 and 0. So if the length of x is n, then 2 to the power n. So here uh, uh, either fx equals 0 for all 2 to the power n possible value, or fx equal 1 for all 2 to the power n possible value if fx is a constant function. If fx is not a constant function, then we can say that fx is a balanced function. So now how we can get this? So if the value of n is 100, then in that case 2 to the power 100, then it is not feasible to figure out whether fx is a constant function or fx is a balanced function by using our classical computing power. So then what? And then how we will figure out? It means the complexity of this problem is exponential. Means up to 2 to the power n minus 1 plus 1 means what is 50%? Means in worst case, let assume in worst case initially 2 to the power n minus 1 time we are getting fx equal 0. After that we are getting fx equal 1. Means after that one more query is needed to decide whether fx is a balance or function, balance or constant function. So means how we will decide the type of the function in quantum computing in polynomial time, just we see. So in balance, fx equal 0 for 2 to the power n minus 1 times and fx equal 1 for 2 to the power n minus 1 time. Now, let the given function fx is either constant or balanced. Implementation of function is a black box oracle. So form of fx is unknown. Now, next slide, please. Okay. So actually, this is the algorithm. By using this, we decide whether fx is constant or balanced. So to certify that a function is constant, it means 2 to the power n minus 1 plus one more query plus 1. A number of queries are needed in classical computing to test whether the type of the function. So actually, in classical computing, it's not feasible. The complexity is exponential. Now, here cat0, just here we are giving two input cat0 and cat0 to head mod gate. Here h tensor h. So cat0 is a input to first head mod gate, and also cat0 the input to second head mod gate. So after passing the cat0 to head mod gate h, what we get? Actually in previous slide we saw that after passing cat0 to head mod gate, we get cat0 plus cat1 upon square root 2. Means that is also called the cat plus. So here we are getting the next state is cat plus for both head mod gates. So means at line A, what will be the states cat plus and cat plus? Means control qubit is also cat plus and target qubit is also cat plus. So after point A, just we are using a one jet gate. So actually transformation I tensor jet is applied to the state cat plus after line A. So actually jet converts the state from cat plus to cat minus. So after converting this, what we get? Cat plus, cat minus. Now target qubit is in minus state. So actually control qubit is same cat plus, but the target is minus. Now after this, now this is the UF function. After line B, there is a UF function. So at step C. So but before step C, just we have to pass this result from this UF function. So here UF is applied to the state cat plus cat minus. Actually, just we get this information from line B. So here, what is this cat plus? Cat plus means cat 0 plus cat 1 upon square root 2 cat minus. Just we give this input to UF function. Then what we get? We get minus 1 to the power f0, cat 0 plus minus 1 to the power f1, cat 1 upon square root 2 cat minus. Here, this is the interesting term. Here, what is this? Minus 1 to the power f0 and minus 1 to the power f1. So if the value of f0 and f1 is same, then we will get the same sign. Uh, so we will get the same sign. It means we will get cat0 plus cat1. Means what is that? That is the cat0. So if the value of uh, value of f0 and f1 is different, in that case what we will get? In that case we will get minus sign between cat0 and cat1. So in the value will be cat0 minus cat1 upon square root 2. So upon square root 2. So in this case we will not get cat0. In this case we will get cat1. So after this, and now come at step D. Before step D, just there is a head mart gate. So just we supply this information. So now if the f0 equal f1, it means we are getting the same sign for minus 1 to power f0 minus 1 to power f1. So here we are getting cat0 as input for this head mart gate. So it means the result will be this cat plus cat minus, and result will be this cat plus cat minus h tensor I. It means cat0 cat minus. Now if f0 is not equal to f1, in that case here we will get the minus sign. It means we will get the cat1. So here the output will be cat1 or cat minus. So just see, if the f0 equal f1, then we are getting cat0 cat minus, and if f0 is not equal to f1, then we are getting cat1 cat minus. Means only one query is sufficient to decide whether f0 equal f1 or not. If f0 equal f1, then we can say that this is a constant function. If f0 is not equal to f1, then we can say it's not a constant function, it's a valence function. The time complexity of this problem in quantum computing is just polynomial. Next slide, please. So actually, this is the generalized problem. Actually, in previous problem, just we took one qubit for control line and one qubit for target line. But here, just we are taking n qubits. So actually, I think it is not needed to go in depth. The logic is same. Next slide, please. Okay. Now we will talk quantum cryptography. So before that, just we will see what is public key cryptography. Actually, in public key cryptography, we use two keys. One is called the public key, another is called the private key. Both are mathematically inverse of each other. If we encrypt by one key, we can decrypt by another key. Next slide, please. Next slide, please. Okay. So actually, first we talk about the RSA algorithm. Then we will see in how we can crack this RSA in quantum computing environment. Actually, in RSA, first we select two large prime number P and Q. After that, we do computation n equal PQ. Here, this n equal PQ. This is the overall strength of the RSA algorithm. After that, we do phi n equal P minus 1, Q minus 1. After that, we select one E parameter that is called the public parameter. And after that, equal by using equilibrium algorithm, E into D, congruent one mod phi n. From this, we get our private key that is called the D. Actually, these are the steps. But overall, what is the strength of this algorithm? The strength of this algorithm is n equal P into Q. So if anyone can get the factor of this n, then easily he can get P and Q. After getting P and Q, he can compute phi n equal P minus 1, Q minus 1. E is the public parameter. So simply he can use the equilibrium algorithm, and simply he can compute the private key D in polynomial time. So actually overall strength of this RSA algorithm is dependent on n equal P into Q. Next slide, please. So this is the encryption. C equal m2 power e mod n. Then m equals c2 power d mod n. This is the encryption decryption. Next slide, please. Next slide, please. Okay. So already I said the overall strength is n equal pq. So here, if anyone can factor p and q from this n, then there is no security in this RSA crypto system. Next slide, please. Okay. So actually, in 94, Saur invented a quantum computing algorithm that is called the Saur algorithm. Before Saur algorithm, just actually in Feb 2020, RSA 250 number means 250 decimal digits or 829 180 has been factored successfully by Boded. So this is RSA 250. If we talk about RSA 1000, so with current computing power, it is estimated that to a factor in number of 1000 digits for this RSA crypto system, it would require much longer than the age of universe. It means by the current computing power, this current classical computing power, it is not feasible to factor n if the size is 1000. But in 94, Saur developed a quantum computing algorithm, and by using that algorithm, this number n can be factored in polynomial time. Actually, there is a dense mathematics totally only for this Saur algorithm. 2 lectures are needed, so just I'm not going in detail. So just just here we can say that by using this Saur algorithm, n equal pq means we can factor n easily. So RSA based cryptographic systems are not safe in quantum computing environment. Next slide, please. Now there is one more important algorithm in quantum computing that is called the Grover's algorithm. So actually, let's say there is a database of 10,000 entry, and we want to search a element. So in average case in classical computing, we will means 5,000 steps are required, and in worst case 10,000 steps are required to get that element. But in by using the Grover's algorithm, means this Grover's quantum computing algorithm, any element can be searched in square root n time. So it means there are 10,000 elements, then square root of these 10,000 means 100. So means only 100 steps are needed by using this Grover's algorithm to search that element. But in classical computing, average steps means 5,000. So if the database is too large, then it is very actually then we can get very good speed by using this Grover's algorithm. But now as we saw that crypto system based on RSA or discrete logarithm problem, they are not safe. Means digital signatures are also not safe, which are based on the RSA crypto system. Actually, due to that Saur algorithm. But symmetric key cryptography algorithm, actually they are safe from Saur algorithm. So by using this Grover's algorithm, so actually here we are Grover algorithm is reducing the symmetric key length, means strength of the cryptographic system. So we can enhance the strength by doubling the key length. By doubling the key length, we can get the same security level. Next slide, please. So in this table, we see that RSA, this is the public key cryptography. So in quantum computing scenario, it's not safe, ECC not safe, but AES, DES, actually these are the symmetric key algorithm. So these are the safe in quantum computing environment. Next slide, please. Okay, so actually we divide problem P and NP in classical computing. So actually there is third category, that is the BQP. So actually BQP is the class of decision problem solvable by a quantum computer in polynomial time. Next slide, please. Okay, now we will talk about the quantum key distribution. Next slide, please. So before that, just we talk about the Diffie-Hellman key exchange. Actually, here there are two parties. One is Alice, another is Bob. So here Alice and Bob compute the common key on open channel. So let's say alpha is the generator and XA is the secret of Alice. So after putting XA on alpha, mod Q, YA, this parameter is passed to Bob, and Bob is doing same thing. He is using alpha generator and he is putting his secret XP on it. And after calculating YB, it passes to Alice. Then both receive the value of one another, and after that they put their secret and they get the same value as alpha equal xa xb, alpha equal xb xa. Next slide, please. So actually, no true randomness in generated symmetric system based on discrete logarithm are not safe under quantum attack. Man-in-mid attack and defilement. Trust on third party in case of digital signature certificate. Also, signature based on RSA or hardness of factorization of integers are not safe under quantum scenario due to SOR algorithm. So actually, therefore, there is a urgent need to design the quantum attack resistant key distribution protocol and digital signature so that next slide, please. Okay. So quantum key distribution. Actually, before this, just we see Heisenberg principle and non-cloning theorem. Heisenberg's uncertainty principle states that it is not possible to measure the momentum and position of a quantum particle with absolute precision. And non-cloning theorem states that it is impossible to make the identical copy of any quantum state. Actually, if you measure that state, then it will collapse and you will get 0 or 1. So actually, it is not possible to clone that quantum state. Quantum cryptography uses the photon particle on different bases for quantum field distribution. Next slide, please. Okay, actually, this is the BB84 quantum key distribution protocol. This is the first protocol which was published in '84 in a conference organized in Bangalore. So actually, here there are two parties, Alice and Bob. So here Alice uses four types of photon: 0 degree, 90 degree, 45 degree, and 135 degree. So actually, orientation of photon actually at 4 level. So randomly she selects the photons and she passes these photons to Bob. On receiving end, Bob uses two detector bases. One is called the rectilinear detector, another is called the diagonal detector. For rectilinear detector, if the orientation of the upcoming photon is horizontal or vertical, in that case, if Bob is using rectilinear detector, then the measurement is correct. But Bob doesn't know what is the orientation photon. So Bob randomly. So sometimes correctly detector measurements then incorrect. So now after passing all photon to Bob, after that Bob he used rectilinear, let's say R for first photon, rectilinear detector for second photon, then diagonal detector for next three photon like this. Now actually for each detector there are two choices, 0 and 1. So if there is any intermediary, if there is any intruder between Alice and Bob, then he will not be able to guess the bit because each detector represent two values, 0 and 1. So then Alice said that this sequence means actually you used these these detector on this number first, third, 7 like this correctly. Other than this, this is the mismeasurement. So actually both discard the mismeasured photon and uh, for which Bob used the correct detector. They keep these bits and they form the secret key for encryption and decryption. Next slide, please. Next slide, please. Okay. So actually, also there are actually एक slide back चला जाइए please. दो स्लाइड मूव हो गए. Okay, now it's fine. Set up an error-free key distributing environment. Actually, this is the major challenge. Actually, mathematically, protocols are secure in quantum computing environment, but the implementation is the major challenge. So, if the measurement of Alice and Bob are not matching with each other, then there is no way to decide whether mismatch occurred due to presence of Eve or noisy or imperfect channel. Lederson also in 2010 proved that in principle BBAT for protocol is unconditionally secure, but secret key can be figured out if the hardware implementation fault. Actually, there are possible attacks, but there are different variations of BBAT for to tackle these attacks. Next slide, please. So actually, in 2016, NIST called the call for proposals. So actually, as we saw that SOR algorithm, this is the threat for public key cryptography, and this is a threat for digital signature. So actually, they called the proposals for quantum attack resistant encryption, key management, and signature schemes. So initially, they received 69 proposals. Out of 69, 26 were shortlisted, and after means out of these 26 shortlisted proposals, 9 were the quantum attack resistant signatures. So after round 2, 3 signature schemes moved to round 3: Crystal, Dilithium, Falcon, and Rainbow. Now, actually, uh, uh, few attacks actually mm, have been carried out on this Rainbow digital signature. So we can say Rainbow is also not the safe. So actually, still we are waiting for the result of round 3. But we have seen the attacks on Rainbow. So finally, a winner will be Crystal, Dilithium, or Falcon. Next slide, please. Okay, now if we talk about the growth of this point, actually, in 98, IBM, Oxford, Berkeley, actually they claimed the development of quantum computing power of 2 qubit. Uh, then if we talk about 278, then DBIP system 28 qubit. So this is the growth of quantum computing. Okay, next slide, please. Next slide. Okay. So, development of quantum computers global scenario. So, actually, in 2018, IBM announced the development of a 53 qubit quantum computer and simulation of 56 qubit design. Actually, on 23rd October 2019, one report was accidentally released, or maybe intentionally Google that released the report. Google has also claimed the quantum supremacy and announced the development of 53 qubit quantum computer. Actually, Google Group also claimed that a task that can be completed in 10,000 years on a fastest supercomputer of IBM has been completed by their 53 qubit quantum computer in just 200 seconds only. So actually, this is the power. So actually, there are many other players in this field: Intel, Microsoft, Rigetti, etc. Next slide, please. Next slide. Okay. So actually, possible applications. Actually, we use supercomputers for doing the faster calculation. So if we can use the quantum computing, and if we can solve the classical computing problems very quickly in quantum computing environment, then we can get the good speed up, and we can solve a time very easily and quickly this problem. So actually there are many applications like the weather forecasting, molecular comparison, and by doing this simulation we can make the good medicines to understand the behavior of deadly virus, optimization of transportation cost, optimal assignment of jobs. Actually there are many applications of this quantum computing. Next slide, please. So actually, as I said, there are many applications area-wise. high-tech, industrial goods, medical industry, finance, and everything is each sector. We can use quantum computers. Next slide, please. Next slide. So actually, broadly, we can divide the quantum technology into 4 categories: quantum communications, post-quantum cryptography, quantum sensing, quantum computing. So in quantum computing, just we deal quantum computing algorithm. In quantum communication, protocols. In quantum sensing, material, device, sensors, device, etc. In post-quantum cryptography for security purpose, we okay. Next slide, please. Okay. So if we talk about the development means country-wise patent application, then we can see the maximum number of patent application in quantum computing are from United States, in quantum cryptography, China, quantum sensors, US, like this. Next slide, please. So actually, in Indian scenario, Indian government has also boosted the quantum research by announcing 8,000 crore in its 2020-21 Union budget for quantum computing over a period of 5 years. Actually, in India, companies like IBM India, QNU Labs, Automatsky, actually these are the players working in quantum computing area. In 2017, DST also launched the ISC Bangalore, TIFR, IISER Pune, RRI Bangalore. So these are the key players in quantum computing in India. Next slide, please. So actually, what is the major challenge? Actually, there are two things. One is the theoretical research, and another is the implementation of that research. So, means theoretical research, it comes under the mathematical area, computer science area, but that implementation, again, we go to physics. So here the point is this: how we can control the quantum particle. So there may be different approaches. So by using these approaches, we can control the quantum computing particle. We can set up the that quantum gate so that the coherence time should be sufficient for operations, so that the gate operation time should be less than the coherence time of that quantum state. So easily we can perform the quantum computing operations. So there may be different approaches like the NMR approach, ion trap approach, nuclear atom approach, optical approach. These are different approach for implementing the theoretical quantum computing algorithm. Next slide, please. So quantum computing challenges actually attacks on public key cryptography system, key distribution, digital signature actually. So by using the SOR algorithm and Grover's algorithm, so these systems can be attacked. So we have to devise new quantum attack resistance signatures algorithm to deal with these algorithms. So a development of reliable quantum hardware devices, development of quantum standards. Actually, there is also a scope in this field. Transformation from classical to quantum infrastructure in the country. Practical implementation of theoretical quantum research. Unethical use of quantum cloud services to break classical system. Skilled manpower in the country. Next slide, please. So actually, MIT also initiated few projects. Design and development of quantum computing toolkit, IIT Roorkee, post-quantum digital signature, document signing sets, Chennai. Actually, other than these projects, actually, MIT also providing the free credit facility for researcher, for professors. They can run their algorithm on simulators as well as on AWS quantum computers. So this is the site at point number 5, setup of quantum computing lab in collaboration of MIT and Amazon Web Services. So in first round we received 21 proposal. Out of 21 we selected 16, and now remaining are in revised state. So here we provide the free credit facility. Researchers use this free credit facility of AWS, and they can do their research, run their quantum computing algorithm. Next slide, please. So future direction, manpower development program need to be initiated at various engineering and science institutes in the country to develop trained manpower in the field of quantum technology. Short-term and long-term course may be initiated to train the students. Content on quantum security may be added in network and security course to develop manpower in quantum programming, training on quantum programming languages like the QSAR, QSKIT, quantum development kit, etc. These can be provided to the students brainstorming session. Next slide, please. Next slide. Okay. So establishment for fabrication of quantum devices, superconducting qubit devices, this is also important area. Focus area should be R&D on quantum materials, quantum sensors, quantum communication, etc. Other than this, quantum algorithm, quantum key distribution, multi-party quantum key distribution, post-quantum digital signature, students can select a particular post-quantum digital signature, and they can go in deep in this algorithm. Parallel Grover's algorithm, quantum language, quantum computer, etc. Next slide, please. Thank you. So, any question, please?
If any of the participants is having any query, you can write in chat box.
Actually, system ने काफी डिस्टर्ब किया और कोई नहीं
सर समटाइम इट हैपेंस कि मतलब कुछ ऐसी चीजें हैं जो कंट्रोल में शायद नहीं रहती.
But the session was very informative, sir. It's really good.
Any
question? If there is no query, then actually my email ID is there. So
if anyone is having any query, you can note down sir mobile number and email ID is there. You can directly write to him, and you can also write to us. We can also route you over there. Okay. So thank you so much, sir, for being here and giving your valuable time. We understand you are very busy because so many initiative, mighty and government, so many work is going on at the back in the government nowadays. So we understand that, but thank you so much for being here. And it was really very informative.
Thank you, sir.
Now only appreciation messages like Ritesh ji have written very informative session.
Thank you, sir.
Gaurav sir, you can put the feedback link now.
Yes, sir. I'm stop sharing now.
Yes, please.
Can I leave, sir?
Yes, sir, you can please, sir. Only appreciation messages, sir. Thank you so much, sir, again. So as usual, as we do, the feedback link is available. Now we'll wait for 5 minutes to fill it. And the next session, sir, can you brief the next session detail, Gaurav, sir?
Yes, already have been given on the group. Next session will be from 2 to 3 p.m. by Dr. Ajit Tripathi. He is senior software engineer in Microsoft. So please be available 10 minutes earlier.
Gaurav, sir, I think link is not working. There's some issue with link. Can you please check it?
It's working.
Please check it. No, there are 2-3 messages, sir. Please check it.
I have checked it.
Now, Sachin is saying it is working. Can you stop?